Good evening, everyone. Let's get started. So, our goals today are to implement the remaining extra region constraints, which are plus and minus diagonals and disjoint sets. And then we're going to implement the clone and palindrome rules. So I've prepared F puzzles set for each of those. So Wormhole 6 Stream is my tutorial puzzle for Sudoku X. You can see these positive and negative diagonals, and the positive and negative diagonals form another set. So if you imagine that and that is a set of 1 to 6, and that and that is a set of 1 to 6. So what we want to do is build those regions if they're present in the JSON. While we're at it, we're also going to support what are called disjoint groups, which you can see here. And what disjoint groups are where that cell, that cell, that cell, that cell, that cell, that cell form a set of the digits 1 to 6. Now, obviously, in a 6x6, this is slightly less powerful than it is in a 9x9, because all disjoint sets have done is rule 1 out of there and there. But, you know, and in fact, there's already 1 there. So all it's done is eliminated 1 from there. But, you know, that's the purpose of these things. I've already programmed in the solutions to these puzzles, and unlike last time, I probably won't first solve them with you. We're just going to see whether or not the solver that we write can get the correct answer. Oh, hello, Peter. Right, so diagonal plus and minus in the JSON show up as plus and minus in the top level. So if we go to the code mode and we take a copy of that and we come back to here and we write into sample puzzles wormhole 6 stream puzzle, then what we can do is start ourselves up and basically jump right in with telling, oopsie, goodness me, I can operate my computer, honestly, telling our program that we want to solve wormhole 6 stream. Now at the moment it's not going to be able to solve it, and we can prove that by doing cargo run, and we panicked. Missing field rule set, line 326. That's interesting. Did I misspell that? Wormhole SIXXTREME. Wormhole SIXXTREME. Let's have a look at the JSON. Pop it back to a tree. I mean, there obviously is no rule set. Oh, interesting. So I didn't bother to enter the rules when I created this these puzzles in F puzzles, because I built them in Sudoku Maker. We're expecting that to exist. So we'll fix that first, because otherwise we're just going to be annoyed with ourselves forever and ever. Amen. So in here, see, we said there must be a title, an author, and a rule set. Let's just allow Surday to put empty ones of those in if one isn't present. I think that's fair, and there's nothing particularly interesting. Kaji loader don't require author, title, rule set in F puzzles. Kaji loader. Okay. Now if I cargo run, it will fail to solve, which is exactly what we're expecting. So let's come back to here and let's think for a moment about that JSON. Pull it up, wormhole 6 stream, minimize the grid, minimize the solution. We've got this diagonal plus and diagonal minus as JSON booleans. So if we remember, anti-king and anti-knight were like that, and so let's do set a default diagonal plus, and positive and negative is the common way of talking about these things. Now, obviously, those names don't match up, so we can do a rename in there. Those are never read because they need to be pub. So we've now got loading in for diagonal positive and diagonal negative. And while we're here, since we're just editing the fpuzzles config, we may as well add the other rule that is to do with regions. And if we just very quickly look at that, it's called disjoint groups. So let's come back to here and let's add a default disjoint groups. Okay, we now need to be able to convert those into our internal puzzle format, which means, of course, we need to teach our internal puzzle format to understand them. So let's pull up Kaji rules. Let's pull up puzzle data. Let's find our Sudoku grid rule data, which, if you remember, is where all of these things are. And we've got diagonal P. We've got diagonal N. And we've got disjoint sets. And I'm going to stick the underscore in there because I think it looks better for us. And those are all booleans and they're going to default to false. So that's good. We just need to write the conversion. So let's come back here and let's pull up the converter. Here's where we add all of these simple booleans. Let's duplicate that for diagonal P. And again for disjoint sets. And it should be disjoint. Is it disjoint groups or disjoint sets? Let's just double check the JSON again. It's disjoint groups. So let's pop back to puzzle data and rename that. Which should have caught it up there as well. Good. So we've got our conversions in place. We've got our loading in place. So the next thing to do is to teach the Sudoku puzzle loader how to deal with that. So let's come along. Rules, Sudoku. So here's where we added the quadruple rule. Here's where we added the anti-king and the anti-knight rules. Now, one thing that we need to remember is that the regions that we need are the rows and the columns and the boxes. So we want to create those regions before we do all of this conversion. So boxes, region ID, that conversion there is where we start to convert rows and columns into the actual regions that we care about. Here's where we convert the rows into non-repeat regions. Where do we convert the columns? We convert the columns beforehand. So we do columns gets converted. Boxes are built from the raw regions that come from our inputs. And then we compute that using... So that's just the conversion, and then this is the conversion for the non-repeat region rule. So do we add a non-repeat region rule for... Okay, so hang on a sec. Let me just work out what we're doing. We've got rows and columns, and we build those up, creating cells. We then say region rows, so these are the regions that we have inserted into the system. Here are the regions for the rows. Here are the regions for the columns. then that's fine. Then we say create the boxes, and we say here are all the regions for the boxes. And then we chain all of those regions together to create all of the non-repeat region rules. So actually it's here that we need to be creating these extra regions, so the positive and negative diagonals and the disjoint sets. So I'm going to go let extra regions is an empty vec, and that will be mutable. If raw rules diagonal n. So the negative diagonal goes from the top left to the bottom right. Then what we want to do is we want to create a region which is all of the cells from top left to bottom right. And we can just do that with something like extra regions push builder add region. And the name is going to be region new. So the name is going to be negative diagonal. And the cells that we're going to have is going to be 0 to self dot size. No, raw dot size. Map given n rows n is the cell index that we care about. It's not extra rectagons, it's extra regions. So there's our negative diagonal. Our positive diagonal is going to be something very similar. So this is going to be diagonal P. And the rule there is just going to be that rather than from n, so rather than going 0, 0, 1, 1, 2, 2, 3, 3, we want to go the other way up. So it's going to be raw dot size minus n minus 1. So that gets us our positive diagonal because we're going from bottom left to top right, and the rows obviously go top to bottom. Then we're going to do disjoint sets. So if raw.rules.disjoint groups, our rule here is that, you know, for every index in the box, we're building a new region. So we're going to go for box index in 0 to self.size, sorry, raw.size. And we're going to go extra regions push. Did we convert the boxes completely? We created box cells by doing boxes.into_iter there. I'm just going to very quickly change that from into_iter to iter. And that should still be fine. No. Type mismatch. Cells iter copied. Right. Just because I want to keep these cell indexes because we care about that. And this one is going to be builder. Add region new, format, disjoint group, b index +1. That's its name. And then the iterator that we want is going to be boxes dot. Oh no. We rename that. That's going to be box cells, just so that we've got that still. Box cells dot iter dot map given the box, or given b, we want b square brackets bidx, and we can close the map. And we should be good. So that's giving us our disjoint groups. So in theory, that adds the two rules that we care about. And then finally, we need to chain extra regions into iter. And that will give us everything that we're hoping for. So if we now run our thing, attempted to insert duplicate for region negative diagonal. Interesting. So it's saying that this region is a duplicate of another region. Wow. Debug time. Let's create the region, which is going to be all the way up to there. Nope, attempting to insert region negative diagonal is the same. Okay. Let's try debug dumping the region just to double check. So it's called negative diagonal. It's got 1, 2, 3, 4, 5, 6 cells, and they're cell 0, 7. Yep. That is the negative diagonal. So why does it think this is a duplicate region? Let's jump into add region. Attempted to insert duplicate for region. Oh my goodness me, I'm such an idiot. We're just duplicating the name. So, diagonals worked, and we can actually see that we used them there in order to solve it. We only used them twice, one in the negative diagonal and one in the positive diagonal, but that was enough to solve the puzzle. While we're at it then, let's go back to main. And let's pick up joined up thinking. Joined up thinking. Something that I am often lacking in. And we can run joined up thinking successfully. Now, naked singles don't act. The naked single rule doesn't tell us which region it was looking at when it did that. So let's just double check that the disjoint regions were needed. And we'll do that by coming into the technique for singles. And we'll include the region name. So we used entirely naked singles to solve this. But what was the region name that told us it was naked? Oh no, it's entirely been done by non-repeat regions, so it can't possibly tell us. Hidden singles could tell us which region it was talking about. We don't have any hidden singles. It's entirely been done by the non-repeat regions, so instead we're going to have to confirm that it's correct by going back to the Sudoku rule and temporarily commenting out the disjoint groups and confirming that it can't be solved without them, which it can't. Good. So we're going to add Kaji rules and Kaji loader, and we're going to commit that with support diagonals and disjoint groups. Okay, so we've done those two. Nice and simple. We didn't need to add any new rules. We just had to load it in and create the regions. So I'm going to get rid of those from here. And now we're going to think about clones. Just to recap, clones are cells where one half of the clone is equal to the other half of the clone. And, you know, we can do that here and here as well. That region is equal to that region. We're also going to be doing palindrome lines, and palindrome lines are essentially a line form of the clone rule. In palindrome lines, one end is equal to the other, so there's a clone pair, there's a clone pair, and when you don't have an even number of cells on the line, then the middle cell is ignored, because it's effectively it's a clone of itself. So there's a clone pair. So effectively, we need to write a constraint, which is this pair of cells are cloned. And then that, you know, then we need to write loaders and parsers for all of that. Or rather, we need to write the loaders and then we'll write the constraint. So just like before when we did the diagonals and the disjoint groups as one, we're going to do clones and palindromes as one and then verify that both of them work. We might not write the palindrome the palindrome implementation before we verified that clones work in the first place, but you know, here we go. So let's write the JSON out for both of these, shall we? Importantly, we can see in Clone Wars we have this clone region, which is a list. It has two objects in. The objects have cells and clone cells. They're lists, which are cell indications. And row 2, column 2 is row 4, column 4. Row 2, column 3 is row 4, column 5. So we can see these in order as the clone pairs, essentially. And then we've got the same here, where we have only one cell. So, you know, in theory, we could have represented that as one clone block with 5 cells, or 6 clone blocks, each with 1 cell. It doesn't really matter. This is how it works. So let's design the load rules for all of this. fpuzzles loader. So we're going to have pub clone, because remember it was singular clone, which is going to be a vector of fpuzzles clones, because there can be more than one clone pair within that. And let's write that down, which is going to be so we're going to derive fpuzzles clones, and in there remember that we have cells and clone cells. So cells, which is a vector of fpuzzles cell ref, and clone cells, which is a vector of fpuzzles cell ref. And just to be sure that we know what we're doing, that's the name in the JSON. Those obviously both have to be pub because it's just data. Like that's pub. And we need to derive deserialize. We don't derive deserialize on that because we have the implementation there. Do we want to do palindrome loading now? Yes, let's do palindrome loading now. So if we look here, we have palindrome, which is a list. Each one is an object. The object has a thing called lines. Lines is a list of cells, or rather a list of lists of cells. Yes. So this is a vec of objects which have the lines, which is a vec of vecs of cells. Yes. Okay. Palindrome vec fpuzzles lines. I'm going to say lines. and we're going to have debug deserialize f puzzles lines, which just has a lines, which was, if we remember, a vector of f puzzles cell ref, which is those. Just seems a bit weird, but you know, there we go. That's what it is. So we've written our loader. Now we need to write our converter, which means that we need to teach the rules set about it. For now, we're only going to do clones. So let's teach our rules puzzle data about clone pairs. Pub clone pair. It's going to be a vector of Sudoku grid rule clone data. And then that is going to be a new thing. So it's going to be deride debug. Oh, I feel like that sometimes. Pub struct Sudoku grid rule clone data. And essentially, it's going to be a pair of cells. It's going to be, you know, what do we call our clones? Let's have a think. Famous clones. Just doing a wee. Oh no, I'm going to be sensible. Why not? We're going to go cell A. We're going to go cell, which is a U size. Row A, U size. Row B, U size. Col A, U size. Col B, U size. So instead, we're going to go, and these are one based. I'm just going to call them A and B because why not? Or, well, I mean, we're always using these tuples, and we might end up writing a function to deal with tuples. So, pub A. And let's do that, mark that again as that, and call that B. So, we're going to do it this way because it matches up with how that works. So if we ever write, you know, deliberately write sort of like a function that does that conversion, we can match things up. Clone 1 Mark 2, Clone 1 Mark 2 version 2. Yeah, I feel it. Right, F puzzles, converter. So that was the givens. That's the solution. This is the quadruples. Let's write the clones. Grid dot rules mute dot clone pairs. We already have that as a vector, and in actual fact, we don't want to just assign it because we're going to be pushing clone pairs in as we find them. So we're going to go for clone group in val dot clone. So that gives us an F puzzles clone, which, if you remember, has cells and clone cells. So the first thing we want to do is we want to assert the equality of clone group.cells.len and clone group.clonecells.len. So we want to be certain that both of the lists of cells are the same length. Assuming they are, we can do that conversion by doing a zip and a map and so on, but you know, we may as well go for it's going to complain about I in 0. No, that's going to complain. It's going to be A comma B in clone group dot cells dot into iter zip clone group dot clone cells dot into iter. So we've got A and B, which are our fpuzzle cell references, and we want to convert those into these A and B, these indexes here. So if we remind ourselves how we do that, we're just going to copy the things across. So we're going to end up saying grid.rulesmute.clonePairs.push Sudoku grid rules clone data A, which is a.row a.col, and B, which is b.row b.col. We've loaded our clone data in. Not exactly hard. So now we can ignore all of that. Let's go and grab Clone Wars' JSON. And then let's change main to load Clone Wars. Now, at the moment, won't be able to do anything. Missing field, palindrome. Interesting. We need to add Serde defaults to those. I'm going to just move this off onto my other desktop so that I can just tab backwards and forwards between the terminal and my editor more effectively. So both of those need Serde default on them. So there we go. It can load the grid, but it obviously fails to solve. Into the rules, we need to come up with a way of adding in our special rule for this, which means we need to write a clone constraint. Right, mod clone, pub use clone. Oh, clone cell. I'm going to call it clone cell because I don't really want to call it clone on the basis that that way madness lies. Create that module and jump into it. Clone cell constraint. Pub struct clone cell. And we're going to have cell A, which is going to be a cell index, cell B, which is going to be a cell index. And for once, we're not going to care about which symbol sets we're talking about, because in my view, if we're dealing with cloning, we want to clone all of the symbol constraints possible, because I don't think it makes sense to say that, let's say, you know, in a puzzle with doublers, that it's okay to have a cloned 2, one of which is doubled. I don't think that's fair. It could be wrong. We may revisit this, but for now, I don't think that's fair. So I think we should be making the clone do all symbol sets. Alternatively, we tell it which symbol set to clone, and later, if we decide we need to do all symbol sets, then the other rules that add new symbol sets will add the clones for those rules. No, because then those symbol sets would have to pass the Sudoku rules as well. No. Derive, debug, decision made. We're going to do all symbol sets for a clone. Impl clone cell. New. Can you guess what this is going to do? Absolutely nothing. Nice and trivial. And I'm going to import constraint for clone cell, and missing members come in. So the things we have to do is we have to say how difficult are we. Clones are in and of themselves not that hard, but probably more than just trivial, because in theory you're looking across the board to find information out. So let's call them slightly easier than quadruples. Quadruples were difficulty medium. So let's go a bit more than difficulty easy. Let's say what they are is their 500 more than difficulty easy. Again, all of these things are going to get tweaked later. Prepping the board. I don't want to do anything here because what I want is to have. Because the thing about prep board is it doesn't tell the caller anything, and I really want the clone's activities to be described. So we're just going to do nothing in prep board, and in logical step, this is where we're actually going to do something useful. So let's pull in what we need, and let's start thinking about how we're going to implement that. But before we do, let's just add all the clone cells in the Stoku rule. For clone in raw.rules.clone pairs. Builder add we need to look up the cell. So let's cell a equal clone dot rows, clone dot a dot 0 minus 1, clone dot a dot 1 minus 1, cell b rows, clone dot b dot 0 minus 1, clone dot b dot 1 minus 1. So we've loaded the clone. Builder add constraint. Clone cell, new cell A, cell B. There we go. Right. Obviously with no action, that should all be nice and simple and still not solve. So here, we're actually going to take a look. And effectively what we want to do is for each symbol pair, for each symbol choice for the cells, if they're not equal, we want to constrain them down to being equal and then report that back. Let mute action equals logical step action self.name. Well, no, it's just going to be clone pair action.push cells some state.cell info self.cell a push str do the same for cell B. So we've prepared our action name, and now we're going to get for each symbol choice, we want to check and do the restriction. So we're going to go let symbols, no, for symbol set in state dot symbol sets. Choice A is state dot choices self dot cell A symbol set. Choice B is that. If choice A does not equal choice B, we need to do a restriction. So we are restricting. New A is choice A and choice B. We're going to go new choice is that. So we're taking the intersection of the choice sets. Obviously, if one is solved and the other isn't, then that would be important. So let's just double check that bit and operation is actually correct. So this does the raw symbol choice bit and operation, and that does this and value mask. So the issue here is obviously that if we were solved before, or if either side was solved before, we lose that it's solved status. So we're going to call that bit. We're going to go let bit equals that. We're going to say solved equals self.0 or right hand side .0 and self solved mask, and it's bits or solved. That just forces the solvedness back in, and we'll have to do the same thing here, and it's going to be self and equals that, self.0 or equals solved. That just ensures that if we were solved before, we stay solved, so that it's not so much of a problem. So we have done a restriction, which means that we have a new choice. And now what we want to do is we want to describe what we are doing, because one or the other or both of these are now restricted in some fashion. So if choice A does not equal new choice, we're restricting cell A. So we're going to say, well, in fact, we don't even need to do that. We can just do it by saying if state dot it's not set symbol, is it restrict regions? Yeah. So if we restrict self.cell A to be new choice, and that changed, then we can say that we've done that. So we can go action.push restricted first cell and I'm going to set but I'm just going to go what do I want to say here, because we're going to do this for every symbol set. Let's just describe the choices, you know, so we can just go, we can say changed equals false, and here we can do blah 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 changed or equals state dot restrict cell A new choice dot changed cell B dot changed, and we can do action. Ooh, let this change equal that. If this change, no, my brain is not operating very well this evening. If either of those changed is true, action.push str or push, yeah, push str state dot symbols. I don't have a symbol set function. That's interesting. Never mind. Let's just say made a restriction. For now. And then here we're going to go if changed return action. So we didn't actually succeed in doing anything. I wonder why. Here we're going to go println choices, choice A, choice B. Those don't implement display, so let's debug them. One clone, two clone, three clone, four clone, five clone. That's the correct number of clones. I mean, those are not the same. Therefore, you know, it does not equal the same. So what happens if we come here and we go choices, leads to, and then we say println goes to new choice. So 6.2 and 3.9 becomes 6.2. Interesting. 6.2 and 3.9 becomes 6.2. That doesn't make any sense. 3.9 and 6.1, 3.9. How is that happening? Perhaps I have misunderstood the priorities on or and. I had. Right. So clones are working now. So we can see like clone pair, row 2, column 4, row 4, column 4 made a restriction. And we'd like to actually get a better explanation of what happened there. So let's try to actually say made a restriction. What actually happened? I'm going to say perhaps, you know, restricted to, and we want to push this symbol choice. So that's going to be action.push symbols, new choice dot options. Is that not right? No, it's not right. No, it's a dot map given symbol state dot symbol symbol. There we go. So clone pair restricted to 632. Different location 632. Pointing cells removed. Clone pair pointing cells. Clone pair restricted to 6. Naked single 6. Naked single 6. So restricting to a single digit really should mark it as solved, I think. I think that would only be fair. So then the naked single message doesn't pop up. So let's fix that while we're here. So this is going to be in puzzle. Restrict does choice is choice mute by set index blah. Choice copy is that. Star choice and equals that. So we're doing an and equals when we do a restrict. So that means again that we should be jumping into the bit and situation here. And in fact, rather than this constant repeat, let's just do self.0 equals self.0 and right hand side dot 0, which I'm going to assume is like the default implementation for bit and assign, but did we actually need it? We did. Okay. So here we go. We've done that, and now we're going to go if bit dot count ones is equal to 1, solved is equal to solved mask. And then, in fact, we don't need that because we're not determining if we're solved in any way other than that. So we're going to go solved is if we do want that, else 0. So that's still doing this naked single statement, despite the fact that we've done that solve. So we said there's only one thing it can be there, which is fascinating. Choice was not choice copy. We propagate changes. Yeah, I don't understand why naked single is showing up, but we'll get there when we get there. The important thing is that it's solved and the solution's matched. So our next goal is to implement palindrome lines. So let's clean up and make some commits first. So Kaji itself, we just improved the intersection rules. So so Kaji rules source puzzle data and Kaji loader is support clones. Kaji rules entirely now. Implement clone cell constraint. Clone wars example puzzle. Okay, so now we want to do the same for the palindrome puzzle, which is this one, back and forth. So let's grab the JSON for that. And cat2 sample puzzles back and forth. Kaji bin. So, as you can see, it can't solve it at the moment because we haven't implemented our whatchamacallums. We haven't implemented the palindrome lines in the converter. So if we pop into our fpuzzles converter, we did our clone groups, palindrome in val.palindrome. We now have an fpuzzles lines. There we go. For line in palindrome dot lines, we now have a vector of cell references. And kind of, if you think about it, what we might have here is we've got like A, B, C, D, E, F cell references, and we want that to give us pairs of A and F, B and E, and C and D. Or we might have an odd sequence like A, B, C, and that needs to just give us back A and C. So we need some way to give us what we're looking for here, which is these pairs back and forth along the line. So if we do for cell A, cell B in line.iter, and we can zip it with line.iter.rev, we now have our back and forths along these lines. And we can just do like we did before. In fact, if I change that from cell A, cell B to just A and B, like we had before, then what I should be able to do is just copy paste that conversion. And we can now solve it because we've got these clone pairs. I call that about half the time I was expecting all of that to take, which is slightly worrying. So let's add that support in. So git commit Kaji loader support palindromes in F puzzles data. Kaji bin add back and forth example. Well, that was more than I was expecting to do, which is a little frustrating, but there we go. So what I think we're going to do next is a little bit of cleanup. Not least of which we still have. We have this telling us that, you know, choices is never read, because we never actually use it for whatever reason. So we could just get rid of it, or because I thought we might need it later. But if we need it later, it's not like we're going to get rid of the computation of it. We're just not passing it in. So that gets rid of that. And what are we missing from now? Here we don't need the symbol choice import. Sorry. Cargo check. Yeah. So it's just Kaji rules clean up quad state. All right, that's that cleanup done. What's the next thing that we want to do? I mean, we could start on value-based constraints. It's going to be a big job to add. And I'll show you what I mean by value-based constraint. So let me pull up, grab our F puzzles again. We'll get a fresh puzzle. I'll do it on 6x6s just because that's easier. If you remember when we went through our constraint list here, we basically said that everything that wasn't palindrome and clone and extra region was a constraint that needed the value of the cells. And what that basically means is that from here on out, when we add new constraints, except for a few that Fpuzzles doesn't support and so I'm not considering for now, we actually need to care about the numeric value of these digits. They're no longer just symbols, they're also value. And a good example of that, and the ones that we will use, are odd and even. So if I pop here and we say, you know, give me a step along the solution path, it's just going to go, all of the digits are available everywhere. If I go ahead and pop an odd marker there and step again, then it's going to say, well, actually, that cell can only be 1, 3, and 5. And, you know, if I odd marked all of those and stepped it, then all of those are 1, 3, 5. And if I clear and step, then we get, you know, this kind of breakdown, and then I step again and we'd get that triple and we're good. So that's how odd digit Sudoku works. For that to work, we need to actually understand that those digits are odd. And typically when you deal with variant Sudoku where there might be modifiers on cells, odd might actually mean the value of the cell. And so if a cell were doubled, it could never be odd. So what we're going to, or you know, if a cell is 0, it's not odd. If there was if there was an eliminator constraint where a cell with, which was eliminated didn't have a value and therefore couldn't contribute to other constraints. So what we're going to do is we're going to write value semantics into our symbols, and then we could potentially do like an odd even Sudoku. And I'm going to say odd even because, you know, that's more fun. So let's grab the even cells, and you know, if we do that and we step again, that's 2, 4, 6. So 1, 3, 5, 2, 4, 6. We get that kind of arrangement, and then maybe, you know, we can stick some given digits in, so we can say that 1, 2, 3, like that, and we can clear and we can say what's the path here, and the path here gets to tell us, well, that's got to be a 5. How did it achieve that? We got a naked. Those are quite a few of those bits and bobs, and then we get, you know, naked pairs happen. No logical steps can be found anymore. None of that is stuff that we don't already support, so we could continue playing around. So, you know, we managed to do 1, 2, 3. Can we manage to do something like 4, 5, 6? You know, clear that. So now we're getting further, but you can see that we haven't actually managed to eliminate anything interesting yet. So let's give ourselves something that might be an interesting elimination. We set that to 4. We've got some more digits. If we set that to 1, naturally, let's set that to 1. See? We've got some more digits, and, you know, we're just going to chase this around a little bit more, because at this point, odd and even aren't interesting to us anymore. We just need to put enough information into the grid that we can keep solving. So we're getting somewhere. We're getting somewhere. We're getting somewhere. We're there. So it's all naked singles, apparently. So let's just, for a moment, come along and take out the odds and the evens and just confirm to ourselves that without those present, we can't solve it. We can. I've given too much information. Never mind. Let's make a new 6x6 grid and try again. Let's have some more fun. So this is why I want this tool, is because actually setting an odd even puzzle, particularly one that's just odd and even, isn't particularly easy. I'm just going to double check whether I have one in my puzzle set. One moment, please. Yes, I do. Copy link. Right. Let's see what this is. Given digits are 5, 2, 3, 2, 4, 6, and 1. There isn't a solution to this yet. if we come along and we say that that digit has to be odd, and we say that digit has to be odd, then we get a whole bunch more information. And now we'll come along and get even, and we'll add in that that digit has to be even. We're not quite there yet. That digit has to be even. And now we have a puzzle that solves. So let's grab the solution and let's give that its correct name, which is strange level. Again, this is one of my tutorial puzzles. I can't believe I didn't remember. Let's look at the JSON. So the JSON, we have odd, which is a list of structures which have a single entry, which is cell, and the same with even. So let's grab that code, and we're going to write to sample puzzles strange level that, and we'll worry about actually loading it in later. What matters first is that we need to work out how we're adding value semantics to our puzzle. So let's go Kaji, source, symbols. So importantly, at the moment, symbols only have a name. Like I said, they're just, they could be fish, they could be cheese, they could be 203, who knows? So we need to add a value to it, but remember that symbol sets might be modifiers as well. So value is not just going to be a number. So we're going to go value, which is a symbol value. And let's implement that. We need it to be debug because, well, that's relevant. And it's going to be an enum, which is going to have set, which is set this particular symbol value. So the digits are all going to be, set 1, set 2, set 3, set 0, whatever. Modifiers that exist that I'm aware of include incrementers, decrementers, nullifiers, doublers, and negators. So incrementers and decrementers can all be represented by an add I32. And nullifiers, doublers, and negators can all be a multiply I32. So that basically gives us everything that we need in order to represent these things. Obviously, to create a new symbol, we're going to need a value, symbol value, and we're going to pass in the value. And now, well, we can no longer convert from strings and from borrow str, so we'll get rid of those conversions, which is going to break a bunch of stuff, but that's okay. And we need to, I would say those should be clone and copy, just because otherwise who knows what's going to happen. And I don't really want these things to be able to be anything but. Value is never read, so let's give a way to acquire the value. So symbol is going to have pub value, which is going to be self.value. And symbol value, let's write an impl for that. So impl symbol value apply, which takes a borrow self and a left hand side, which is an I32, and gives back an I32. And it's going to be so if we set n, we give back n. Add n, we give back left hand side, plus n. Mul n, we give back left hand side, times n. So we now have some way of thinking about symbol values, but of course we have a problem, which is that in puzzle data, we can't construct our values. So we can't do symbol new, symbol.display. We also need the symbol's value. So symbol data, let's just jump into that for a moment. Where are we? Symbol data only has a string, so it's going to have a value, which is a Kaji symbol value. And we'll get there in a moment. But now we can do symbol.value. Why do I bother with that? But I don't know. Perhaps in case I don't have it by ownership. So let's come back to the edit that we did and stick the brackets on it. So that's fair. And now we have an error here, which is that symbol data obviously can't be created without a value. There we go. So now we've taught puzzle data about symbol values, and now we have to teach these loaders about symbol values. And the value in each case for these is quite simply symbol value set n. What have I cocked up? Mismatch types. Expected in I32, found a U size, n as I32. And in the F puzzles converter, we're going to need the same thing. There we go. So we've got, as it were, the value stuff plugged in. So the last thing that we need to do is we need to teach the puzzle, or rather the board state. So impl, here we go. So solve state here, for example, has things like, you know, what are the choices in this location on the board? What's the symbol for this symbol ID? What we want to do is we want to say what, you know, given a cell index, what is the cell's value? So we're going to go pub fn cell value z. So yes, takes a borrow self and a cell, and it gives back an impl iterator item equals. Now, do we want to give back just the values that it can be for now? I think what we want to do is we need to give back the symbol combinations and the values that they have. So item is actually going to be cell value. And we're going to have to design that. Okay. So what I'm imagining here basically is that a cell value is so a cell value is the set of symbol choices, or rather the set of symbols and the cumulative value that results. So there's going to be symbols, which will be a vec of symbol ID, and value, which is an I32, and those can both be pub. Well, no, we'll make them not pub, and we'll deal with that later. So here, what we're going to do is we're going to say that effectively what we need to do is we need to get all of the symbol choices at that cell index, and then do the whatchamacallit, like the multiplicative combination of it all. I don't know how hard that's going to be, but let's get there. So let choices equals board dot choices cell dot collect as a vector. Right. For now, I'm just going to go like that to shut up the vec is not an iterator. No, but now we've got that, which means that we're getting somewhere. The cell values, as it were. So we've got these choices, which is a vec of raw symbol choice. So each entry in that is the set of choices that we can have, but there's an arbitrary number of those. So how are we going to deal with making choices? Crikey O'Reilly. I think we get to do this by recursion, which is really, really grungy, but never mind. Let mute ret equals vec. And then we go self dot cell values. Ret borrow mute ret choices dot dot. Which borrow choices. Pub fn cell values self ret, which is a borrow mute vec of cell value, and choices, which is a borrow raw symbol choice. And we also need a current value, which is an I32. And we pass a 0 in for that. Okay. No, it doesn't need to be pub. Right. So what we're going to do is say, nope, 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 that's still not good enough. We also need a symbols, and we're going to pass borrow mute ret, borrow mute symbols, borrow choices. Symbols is a borrow mute vec of symbol ID. Okay. And we're actually going to restrict choices backwards rather than forwards. No. We're going to pass choice n, and we're never going to restrict choices. So we want you to pick the 0th choice, and we're going to go here. We're going to go if choice n is choices.len. We've completed a set of choices. Return this value. Ret.push cell value new borrow symbols and curval. And then we're going to hit it to do there. And of course, cell value doesn't have a new. So let's just come up here. We've got an impl effect. We're going to have impl cell value. So new takes some symbols, which is a borrow symbol ID, and a value, which is an I32. It returns a self. Which does that. And back down here. Right. Type notation arguments must be elided with ... Silly me. There's my typo. Okay. So what's it whinging about? Choice n needs to be a usize. Creates a reference is immediately dereferenced. Yes, that's fair. Writing borrow mute vec instead of borrow mute thingy involves a new object where a slice will do. Is that true when I'm actually going to be pushing and popping symbols? I don't think so. On the other hand, it is going to be of the correct length. So symbol ID choices len. Pretty good. Cannot initialize a tuple struct. Symbol ID new 0, 0, because we don't actually care. Right. Okay. So we know that we're now trying to do making a choice through the choices entry that we care about. So we're going to go for opt in choices choice n dot options symbols choice n is equal to symbol ID new choice n opt. So that is, at this point in the chain, this symbol is what we're choosing. So we've made our choice, as it were, for choice n. And then what we're going to do is we're going to go self.cell values. We continue to pass ret. We continue to pass symbols. We continue to pass choices. We're going to pass choice n plus 1. And we are going to apply this symbol's value to curval. So this is now going to be self.puzzle.symbol symbol symbols choice n dot ID Two IDs. Symbol ID, no. Do we not have a thing that takes this symbol ID? New val. So symbol is that. And we want the symbol info, which, as I recall, yeah, we just have dot symbol, which is just self.puzzle. So self.symbol bracket symbol ID. So self.symbol symbol dot value dot apply curval is that. Okay. Woof. I mean, that's grungy as heck, but there we go. We don't have a dot. We've got solved for the entire board. That's fine. So what cell values tells us is it tells us that if we want to get the values for a cell, which might be only one value, it might be lots of values, we don't know. We get told all the different ways that we can make those values. We get told, you can be this value by this combination. Okie dokie. Right. And then what we get to be able to do then is we get to eliminate things if we don't want them. Ooh. I mean, I don't know about you, but I'm struggling a bit. We'll get there. We'll get there. Let's do odd even. I mean, let's just go. There we go. So I added my new puzzle, strange level. So let's load strange level. And let's write our loader support in a bit. First of all, I'm just going to git commit add symbol values. Kaji. Support symbol values. Right, so now we're back down to, we've just said we're going to load strange level, and if we cargo run that, we will fail to solve it because we don't have enough information. Okay. Half an hour. Are we going to manage to do odd and even in half an hour? We might. You never know. Just give me one moment. Sorry about that. Okie dokie. Let's see. We want to write odd and even. In F puzzles, as we said, that shows up as odd, which is a list of objects which have a single entry called cell. So let's see how we're going to do that in our F puzzles loader. So we don't have a struct that can do that already. So let's go serde default pub odd, which is going to be a vec of F puzzles single cell. And we're going to repeat that for even. So F puzzles single cell needs defining. pub struct f puzzles single cell, which has cell f puzzles cell ref. And that needs to be pub. And then we need to add those odd and even rules into our rules puzzle data. Rules data, okay. Pub odd cells, which is going to be a vec of usize. Even cells, a vec of usize. And because we have this as our tradition, let's make sure that we have those. And then if we come back to our fpuzzles loader, guess what? For odd in val.odd, grid rules mute odd cells push odd.cell.row odd.cell.column, and repeat that for even in val.even even cells. So that's now inserted the odd and even stuff into our puzzle data object. So we're done with the loader. We're going to need to write a constraint. Now, if we only ever had one symbol set and it was only ever the Sudoku digits, we could do this entire thing with the basic implications. But because we want to support variant puzzles, we can't do that, because we have to think about values rather than symbols themselves, which means we're going to be writing a constraint for this. So let's define our constraint. So we're going to go mod odd even pub use odd even. Create the module, jump into it. Odd and even cells. Oh, hey Lugnuts. So we've moved on because we got through palindromes and so on a little bit more quickly than I was expecting. So we're now trying to do odd and even cells, which is just made difficult by the fact that up until now, we haven't had the concept of values in cells. And I mean, even now, we're probably going to do a very dodgy implementation of odd even. That means that later when we actually add variants, we're going to hit a panic or a to-do or something in here. But we'll get there. So we're going to import odd even pub fn new cell. And I'm just going to say is odd boolean so that we can pass that on, and then we're going to import. See, let's grab that out of Kaji. Constraint for odd even. Missing members. Difficulties for odd even, I think, is just easy. Or is it me? Because we're talking about values that might be. Let's go for this is easy plus 250, which makes it slightly easier than clones, but still harder than the like hidden triples and things like that. Prep board. We're going to do nothing, again, because we want to make sure that every time we do something because of the odd even constraint, we actually say that we're doing it. And so logical step is where we're going to do our work. And that happens as follows. The first thing that we're going to do is we're going to find out all the possible values that our cell could have. So we're going to say let values equals state dot cell values self dot cell collect as a vector. If values dot len is greater than 1, well, is less than 2, return logical step no action. So that's our easy exit for, well, there's only 1 or possibly 0 because something got broken, but we detected that elsewhere, value that this cell can be. So there's no point worrying about it. Otherwise, what we want to do is we want to eliminate any value from this cell that we shouldn't have. So we're going to go action equals logical step action self dot is if self dot is odd else even. So that's just doing the format, and then we go action dot push cells sum state dot cell info self dot cell. Right, so that's going to tell us what symbols we end up eliminating. Now what we're going to do is we're going to make the rash assumption that we're only ever dealing with a singular symbol set for now. So we're going to assert equal values 0, because we know there's a value at this point. So value 0 is a cell value object, and we want to say, dot value. No, sorry, we want to say dot symbols dot len is equal to 1. And that's going to complain that symbols is not found. So now we're going to get to implement that, which means that we get to come back to Kaji puzzle up here. Pub function symbols, borrow self, borrow symbol ID, self symbols, value, self value. So we're now going to get through all of that. I apologize for the baboop. I will just mute Discord. There we go. So for now, we only support odd even when there are no modifiers. So we're just making sure that we're only operating in the singular constraint here. And what we want to do is we want to find out, because if any of those values are not odd or even, depending on our setting, we want to eliminate that symbol from the cell. For value in values, if value dot value and 1 okay, that is odd equals that. And now all we want to do is eliminate if it's odd and we want even, or if it's even and we want odd. So we're going to go if is odd does not equal self dot is odd. We need to eliminate these symbols from this cell. And so the way that we can do that is we can say, oopsie, let mute elims equals a vector. And now we're going to go elims push value symbols 0. State eliminate cell values symbols 0. So that's just, it's doing the elimination, and we know that that symbol must be present because otherwise it wouldn't have shown up in the values list. And then here we can go if elims does not if not elims is empty. We've done some eliminations here, and so we are going to say that action push symbols elims into iter map the symbol to state.symbol symbol return action. What have I fluffed? Missed one close paren. Not values, value. So we've now got our odd even, a very basic odd even implementation. It's very dodgy, and we're going to hit that assert the moment we start to try to write a variant, but it's good enough for now. I'm going to try and find someone who's got a doubler or something variant which uses odd evens and the other constraints that we already have and nothing else, so that we can actually test this. What are modifiers? So modifiers in my mind are, for example, doubler rules or negator rules or nullifier rules, things like rules where you end up with cells that have been modified in some way that affects their logical numeric value. So like, if you imagine a cell is doubled, it can't possibly be odd. So if you had an odd mark in a puzzle that had doublers, you would know that that cell could not be doubled, as well as that it had an odd digit in it. But if you had an even cell, you wouldn't know that it necessarily only had an even digit in it because it could have a doubled odd digit. Does that make sense? Hopefully it does. And I'm going to get told that doublers don't affect odd even, but I think they do. And as far as I'm concerned, we're going to assume that they do for the rest of this, because it really matters when we start to do things like killer cages or arrows and so on, because they really, really are affected by that. Annoying to program, indeed, very annoying to program. Fortunately, this solver is not meant to be in any sense quick. So by not needing to be quick, I get to be really grungy in the way that I do things, like, constantly creating and destroying arrays of things and doing mathematics on stuff that realistically I don't need to do, because ultimately it doesn't matter if it takes it 10 seconds to solve a puzzle. Logically, that 10 seconds is still going to be way faster than a human being. And what I want this for is to allow me to build puzzles that I can use to introduce techniques to people or to introduce rules to people in a tutorial level. If I want something that does true candidates and brute force solving and so on, then there exists plenty of solvers that I can use for that, including like the one that's built into Sudoku Maker. Right, so we've got our odd even. Let's now add support to here. So we're going to go for odd in raw rules odd cells builder add constraint odd even new rows odd dot 0 -1 odd.1 minus 1 is odd true. And then we can duplicate that, and we can say that's even, and that's for even cells, and is odd is false. So in theory, that's added odd and even support. I fully expect this to either crash or fail. It crashed, hooray. Len is 1, but index is 1. Fair enough. Yeah. So we've screwed something up, but that's fine. Let's chase down what we're doing and find out. We're almost certainly screwing up either in cell values or in something else. So we're talking about puzzles.rs line 751. One day I'll learn the key press for jump to line. Yeah, so we're computing cell values and we've squiffed up somehow. So all I'm going to do first of all is I'm just going to go choices, choice N, curve L. Control G, is it? Oh, so it is. Thank you very much. I'll forget that momentarily, but that's fine. And it's going to complain that cell value does not implement debug. Does now. Okay. So we came in, ret was empty. Control P to jump to file as well. You see, I'm just so slow. So ret is empty, which we expect. Symbols says 0 because obviously we haven't chosen anything yet. And the raw symbol choice at this point is 4-3, whatever that turns out to mean. We're making choice 0, current value is 0. Move on, we've got nothing there. Symbol ID 5, so we're choosing ID 5. We've set the value to 6, and we are choosing at 1. Now 1 is equal to the length of choices, so what I've missed is a return statement there. We're getting somewhere. Interesting. Okay, so let's get rid of that println because we're getting closer, but what we're not being told is that there's any eliminations happening because of odds and evens, which is interesting because if we look here, we've said, okay, whatever cell that was, we haven't got anywhere. So let's go to our odd even constraint. And let's say here, println cell self.cell could be values. Yes, not supported. Of course it's not. Consider using extract that expression, please. Thank you. Okay. So we're getting empty lists back. That's the problem that we've got, is we're getting empty lists back. I like this, Control P, thank you very much. Which is interesting because we're pushing into ret there. Oh, for pity's sake. We're not returning it, are we? No, that would be too easy. I'm really good at this game, aren't I? And now we solve the puzzle. Hooray! Odd even and the basics of cell values now implemented. We haven't got any dodgy printlns there. Let's get rid of the printlns from there and let's have a look at what we're actually told. So, odd cell at row 2, column 3 eliminates 6, 4, and 2. Correct. Odd cell at row 5, column 4 eliminates a 4. Even cell eliminated a 1. Even cell eliminated a 5. So that's 1, 2, 3, 4. So that's all 4 of the constraints that we had in the puzzle have done their work. Everything else is naked or hidden singles, except for a little bit of pointing here. And in reality, I think if we say that instead of being easy 250, it's trivial 250, then we may even get away without pointing cells. Yep, we don't even need the pointings if we apply the restrictions earlier. So we only have hidden singles, naked singles, and the odd and even operations. And that solves the puzzle. Yep, I think I like it being trivial because that's good. Remove the unused import. Right, cargo. Clippy, make sure I've not got any warnings left. Okay. Add concept of values to cells, to symbols / cells. Kaji. Hang on. That's just fixing it. Git log. Yeah. Git commit fix up. No. Amend. Okay. Git commit -ss kaji rules loader support odd even in puzzle data. So that's going to be kaji loader, and it's going to be kaji rules source puzzle data. Kaji rules add odd even constraint, very basic for now. And then we can do git add, git commit, kaji bin, add strange level sample. Right, that's added odd even. We've added the concept of values in. I think at this point I'm going to call it, even though we're about 7 minutes early. But what that does mean is that next time we can think about some more value-based puzzles. So if we think about that, you know, non-consecutive is an example of a global constraint where you can't have consecutive values in cells. I'm going to assume it's values, but if anyone's ever made a non-consecutive puzzle with, you know, doublers or negators or what have you, please do let me know, because I think that would be fascinating. Or, you know, we could now start to think about implementing, say, Renban or German whispers or arrows, something where we can start to think about things according to the values of the cells rather than anything else. For now, like I said, I'm going to call it there. Thank you very much, everyone, and I will see you next time.